Swayam Prabha. Digital India. Educated India.
So in yesterday's class, we were looking at a problem of a gas bubble in a quiescent liquid. Okay, this is a gas bubble in a quiescent liquid, and there were far field pressure oscillations. P equal to P0 plus PA sin omega t, where P0 was the equilibrium pressure, okay, and PA is the oscillation amplitude of the pressure. So initial conditions are P0 plus 2 gamma by R0 will be equal to the pressure inside the bubble. This is a simple Young's Laplace equation. Okay. So the motivation for this problem was we were considering undesirable gas bubbles in heavy machinery like reciprocating pumps. On the event that the bubble is really small, this pressure oscillation will mimic the motion, to and fro motion of the machinery like a reciprocating pump. Okay. So we were interested in finding the dynamics of such a bubble. That is why we are considering far field pressure oscillations on a gas bubble. So the governing equations that we came across are governing equations we used so far were the Navier-Stokes and continuity equation and continuity equation. Okay. We assumed that the bubble only undergoes radial oscillation, which means that assumptions are unidirectional flow in radial direction. So this means that UR is a function of radius, radial coordinate and time. U theta and U phi are 0. There is no velocity in the theta and phi direction. Also, there is no variation in theta and phi direction. Okay. So no variation in theta and phi direction means that the interface of the bubble has no deformation. No deformation. So equation of the bubble at any given time we can write as R equal to R of t, where capital R is the radius of the bubble that changes with time. Okay. So in last class we used the continuity equation to find that UR is given as h of t by r square. Okay. Then we used one of the boundary conditions. So the boundary conditions for this problem are kinematic boundary condition, normal stress balance. Both are applicable at the interface, which is R equal to R of t. So we use the kinematic boundary condition. Kinematic boundary condition states that any fluid particle on the free surface or on the interface, any fluid particle at the interface does not leave the interface. So this translates into the material derivative of the interface being equal to 0, where F is the interface equation. Okay. Here f will be equal to r minus r of t, r equal to r of t. So, interface equation will be r minus r of t. Okay. So, this was the kinematic boundary condition. I will call it as KBC. Okay. So, we used this kinematic boundary condition to find value of h of t, and we found that ur is r square r dot by small r square, where r is a capital R is a function of time. So, after this what we did is we substituted this u of r in the Navier-Stokes equation. So far we know that the radial velocity varies with distance from the bubble. So, we know that it varies with distance from the bubble and it varies with time. So, we seek to find the variation of the velocity with respect to time alone. So, we need to express the Navier-Stokes equation in terms of this r square r dot by small r square. Okay, so, we substituted this value in the Navier-Stokes equation and we simplified the equation, followed by integration along the liquid domain, and finally we got one expression. Okay. So, we got r double dot plus 3 by 2 r dot square is equal to pressure in the liquid side at r equal to capital R minus pressure far away in the liquid side divided by rho. So, we did till here last class. Is it clear? Okay. So, now in this class what we will be doing is, we do not know the liquid pressure at any given time. We need to find P liquid at r equal to capital R of t. So, we need to find the liquid pressure close to the interface. So, for this I will explain the algorithm of what we are going to do. Okay. So, to find this we will link the pressure in the liquid at the interface for any given time. We will link it to the pressure inside the bubble at any given time. Pressure, so I will call it P bubble at any given time using the normal stress balance. Okay. Balance. Then we will find this pressure inside the bubble at any given time using the initial pressure inside the bubble. Initial pressure inside the bubble. How we will link both these is, so we assume that the process is isothermal. So, the gas inside can be expressed using the ideal gas equation. Okay, we will use ideal gas equation to relate the pressure at any given time using the volume to the pressure inside the bubble initially. Okay, we will do this today. So, first thing is we need to do the normal stress balance at the interface. Okay, normal stress balance. So, we know that the interface only changes the radius. Okay, there is no interface deformation on the surface. Okay. So, this allows us to do the normal stress balance along the interface, knowing the interface equation R of t. We know that the normal component everywhere at the interface is what? The radial component r, always it is small r. Okay. Normal component is always small r, because the bubble does not deform, it just changes the radius. So, everywhere at any given time the radius is, the radial component is the normal to the interface. Okay. So, we will do a small normal stress balance. So, which means that the normal direction, the forces normal direction forces are balanced. Okay. So, from the liquid side, the stress is given by sigma RR. Okay. This is the pressure exerted by the liquid on the bubble. You add from the liquid minus sigma RR from the gas. Okay. This will be equal to the surface tension force 2 gamma by R. So, both are measured at R equal to capital R. So, what did I do? I balance the force from the liquid side and the gas side using the surface tension at every given time. A basic force balance in the normal direction. Okay. So, this sigma RR means the force in the, so force acting in the plane which has a normal component small r in the direction small r. This is the direction and this is the element on which it acts, the normal to the element in which it acts. So, here normal stress balance, so both are sigma RR. Okay. So, sigma RR from the liquid side will be given by negative of the thermodynamic pressure. So, we will call it P liquid. So, it is PR. Okay. I am calling it as PR at R equal to R plus tau RR, where tau RR is the viscous stress at R equal to capital R for the liquid side. Okay. This is both are on the liquid side. So, this will be P of R plus 2 mu dou UR by dou R at R equal to capital R. Okay. Now, coming to the gas rate. So, tau RR at gas side is given by again negative of the thermodynamic pressure. So, we will call it PG. Okay. Sorry, not PG, PB inside the bubble. Okay. At any given time plus tau RR at for the gas, okay, at R equal to capital R. So, in our assumptions, we assume that the gas is inviscid. Okay. So, what happens is this, so I will call it UL. Okay. So, 2 mu G here is 0. So, that is why it not applicable here. This term goes to 0. Now, we will substitute both these values there, okay, in the normal stress balance. What we will get is minus P R plus 2 mu L, I will call as mu because that is the only significant viscosity here. The gas is inviscid. Okay. So, gas is inviscid. Okay. 2 mu dou UR by dou R plus. So, we have to subtract this with gas. Okay. So, this will become plus PB of T, okay, is equal to 2 gamma by R. Okay. Any doubts so far? All we did is we balance the forces at the interface, normal forces at the interface. Okay. So, now you have to substitute the UR value that we got. I rubbed it away. So, we got UR is equal to R square R dot by small r square. Okay. Substitute this here please and put the value R equal to capital R and tell me what you get for this viscous term alone, tau RR. Please do it. Just this expression, what is 2 mu dou UR by dou R, substituting this value. So, we get minus P. So, this is the liquid side pressure at R equal to R. This is also a function of time, do not forget, okay, plus, oh sorry, she said minus, right. So, minus 4 mu R dot by R. Everybody got this? Okay. Plus P bubble at any time. This is the pressure inside the bubble at any given time. So, as I said, this pressure inside the bubble at any given time, we will relate to the pressure, initial pressure inside the bubble using ideal gas equation, because we assume that the process is isothermal. Okay. So, this is equal to 2 gamma by capital R. Okay. So, this is an expression that we need to find out, right. We need to find the liquid pressure at R equal to capital R. We have an expression for this. So, we know from normal stress balance that P liquid at R for any given time is given by this Pb at any given time minus 4 mu R dot by R minus 2 gamma by capital R. Okay. It's clear so far? Any doubts? Okay. So, now our objective is to find this, because we do not know the pressure of the bubble at any given time. So, we will relate the pressure. So, before this, since the process is isothermal inside the bubble, since process is isothermal, there will be two pressures inside the bubble. So, at any given time, the pressure inside the bubble can be given by the vapor pressure at that temperature, okay, plus any undesirable gas that is present. So, we will call it Pg at any given time. Okay. This is time related, this is temperature related. So, this is a constant. The vapor pressure is a constant. However, gas inside will vary according to ideal gas law. Okay. Clear so far? So, this gas, so using ideal gas law, pressure initially, okay, I should write it as Pg initial into initial volume of gas or initial volume of the gas inside the bubble. Okay. So, initial volume of gas inside the bubble, so I will call it as V initial is equal to P gas at any given time, this one, plus into volume of gas at any given time. Okay. What I am doing is I am relating this pressure of all the trapped gases inside with the initial pressure inside using ideal gas equation. So, Pv equal to a constant for Pv equal to nRT. Here all others are constant, isothermal process. So, Pv equal to a constant. That is why we can write like this. Okay. So, initial gas pressure, initial, what is the volume of the bubble? Initial volume of the bubble? Four by 3 pi R0 cube. Okay, is equal to into 4 by 3 pi r cube, where r is a function of time. Okay. Volume at any given time is 4 by 3 pi r cube, where r is a function of time. Okay. So, we can write an expression for this. So, Pg of t is given by, you cancel off all the constants, you will get Pg initial r0 by r the whole cube. Okay. Yes, that I will explain. So, we got it in terms of Pg initial. Okay. So, what we can do to find Pg initial? Initial gas pressure inside the bubble. How did we find the gas pressure inside? Using normal stress balance. Okay. So, we will do normal stress balance in the initial condition. Okay. That is just Young's modulus. Okay. So, we will use the Young's Laplace equation. So, to find initial gas pressure, Pg initial, we do normal stress balance at initial condition. Okay. So, initially we know that the pressure inside the gas is balanced by Pg0. Okay. That is the initial pressure, P bubble, Pb0. Okay. Pressure inside the bubble is balanced by the pressure outside plus 2T by R0. Just Young's Laplace equation. Okay. In this case also, the inside the pressure is varying as two components, which is this, the vapor pressure and the gas pressure. Okay. So, initial gas pressure plus vapor pressure is equal to P0 plus 2T by R0. Now, we have all the pieces. Okay. So, we found the initial pressure inside the bubble. Again, we used normal stress balance at initial condition. So, we will use it to find the initial gas pressure as a function of ambient pressure. Okay. So, here the ambient pressure is P0, that was what was balancing the bubble to be stable. So, now we have a couple of equations we need to resubstitute backwards. So, what we will do is, we will substitute this Pg of t here, okay, and then substitute this Pb here, and then we will get the Rayleigh-Plesset equation. Okay. That is the main algorithm to find the P liquid at R equal to R of t. We used normal stress balance again to find the pressure as a function, as a component of this pressure of the bubble at any given time. Then we related it with the initial pressure using ideal gas, and used normal stress balance at the initial condition to find the gas pressure as a function of initial gas pressure. Okay. So, what we have here is P liquid we know is this. Okay. Now, what we have to do is we substitute all these backwards. Pb of T is Pv plus Pg of T, which is given by that. So, Pg0, I will call it as Pg initial into R0 by R the whole cube. Okay. I just substituted this, which is the gas pressure at any given time, onto the this equation to get the bubble pressure at any given time. You should know that PV, which is the vapor pressure, is a constant from the beginning, from the initial condition to whatever condition that we have, because the problem itself is isothermal. So, it is like an addition, like an additional pressure inside the bubble. Okay. So, we have this, and then now we need to substitute the value of Pg initial, which is this, okay, onto this equation. So, we get Pv plus P0 plus 2T by R0 minus Pv into R0 by R the whole cube. So, all this we are doing to get an equation which is only dependent on time. Okay. All these variables P initial, P, G, all this we have converted into a set of constants and some variables which are dependent on time. So, now we can solve an expression completely which is only dependent on time and some constants that we know. That equation as such is called Rayleigh-Plesset equation. Okay. So, this is the Pb of T, or the bubble pressure, a pressure inside the bubble at any given time. Now, this we need to substitute here to get the liquid pressure. So, we substituted the initial gas pressure back in the gas pressure at any given time. Then we substituted the vapor pressure and got the bubble pressure. Then we are substituting it back into the liquid pressure to get the liquid pressure close to the interface. That was our main objective. So, we had R double dot plus 3 by 2 R dot square is equal to P liquid at R equal to R minus P infinity, because we integrated from R equal to R to infinity, P infinity by rho. Okay. So, our objective to do all this was to find the liquid pressure at R equal to R, that we have found. So, if you substitute this Pb of T here in the normal stress balance, you will get the expression for pressure of the liquid just outside the interface at any given time. Okay, minus 4 mu R dot by R minus 2 gamma by capital R. Is it clear so far? Everybody are okay. Now, we have got the Rayleigh-Plesset equation. Okay. So, R double dot plus 3 by 2 R dot square is equal to, so I will substitute this there. Okay. We know P infinity is, so in the initial problem definition we had it as ambient, equilibrium pressure plus Pa sin omega t. That was the far field pressure at any given time. So, we will get Pv plus P0 plus 2T by R0 minus PV R0 by R the whole cube minus 4 mu R dot by R minus 2 gamma by R. So, the entire thing minus P0 minus PA sin omega t by R rho, okay, the entire thing by rho. So, what do we have here now? We have an second order ODE, okay, second order non-linear ODE which we can solve to get the radius variation with respect to time. All other things are constant here, we know all of them, okay. Oh, I wrote this as T, it is gamma surface tension, okay. So, we will first just describe some characteristics of this equation. Okay. So, looking at it, it looks really complicated. So, the equation as such. So, this is a second order non-linear equation, second order non-linear because of this R. Okay. So, one thing you can notice quickly is suppose at t equal to 0. So, at the initial condition t equal to 0, can anybody find the value of the equation? Just put t equal to 0. At t equal to 0, bubble is at rest. So, R dot will be equal to 0, okay. R will be equal to R0. Can you substitute it? Let me know what you have, and of course, acceleration will also be 0, okay. Bubble is at rest, and that PA sin omega t won't be there. Nothing, the equation should be 0, 0 equal to 0, okay. Okay. I was just checking whether you are paying attention, but yeah, okay. So, so again we need to solve the second order non-linear equation. So, how we do this is we can use some computational material like MATLAB or Mathematica and split this second order ODE into two normal ODEs, okay. How we will do this, I will explain. So, remember these initial conditions, initially R is equal to R naught and R dot is 0, which means the bubble is initially at rest, and then you are applying the PA sin omega t, okay. So, this is our equation that we need to solve, R double dot, okay. Clear so far? So, now, so to split this into two normal ODEs, what we can do is we will substitute, suppose x is equal to capital R, okay. We should know that R is always a function of time, okay, capital R, and y is equal to x dot or y is equal to R dot, okay. Both are same, okay. Now, you substitute this here and let me know what you get, which means you are substituting R dot as y and R as x, okay. I hope you can see the equation, okay. So, what we will get is actually two ODEs, one is y equal to x dot Okay. As you can see here, this one y equal to x dot, other is y dot is equal to 1 by rho x of this. All we are doing is we are writing r double dot is equal to r by this expression. Okay. So, I have to write the entire thing again. Omega t minus 3 by 2 r dot here is y. Okay. So, before that I will just write the expression. Okay. R dot square by r. Okay. Everywhere there will be r by r. Okay. And r dot we are writing as y. Okay. So, if you do this, you will get two ODEs like this, or two ordinary differential equation of this form. Okay. Now, what we will do is we will use a computational device like MATLAB or Mathematica and solve both of these simultaneously, giving an initial condition that y of t, right. So, y of 0 is 0 and x of 0 is some r 0, which is the initial radius of the bubble. Okay. We will explain the MATLAB part maybe in some tutorial, I guess. Okay. So, what we will get is, so I will just write the two ODEs. So, we know these, right. So, suppose we are going to write both of them as ODEs, we can write them in a matrix like d by dt of these both, right, x comma y will be equal to, suppose I call that as y and this big expression. Okay. I will call this as f of r, or this will be f of x. So, we will input this as a matrix into MATLAB with initial conditions at that x is r 0 at x is r 0 at t equal to 0 and y is 0 at t equal to 0, and then we will solve the equation. So, what we will get are some interesting curves, we will see. So, this is one of the bubble radius variations with respect to time. So, here we are oscillating with the frequency of 1 hertz. So, omega is 2 pi into 1. Okay. Here always omega is 2 pi into frequency. Okay. Angular frequency is related to frequency as 2 pi omega. 2 pi s. And initial bubble radius is 2 mm and amplitude of pressure is small, that is 10 kilopascal. Ambient pressure, initial pressure is just atmospheric pressure. Okay. Vapor pressure, all these are taken for a gas liquid system, air water system. Okay. All other parameters are taken for a air water system. So, here what we see is the bubble is purely oscillating. So, you see that the radius is varying sinusoidally with change in pressure. You will see that the bubble increases in size, reaches a maximum radius and then reduces, goes below the initial radius, then comes back up. Okay. Now, suppose we decrease the bubble radius, suppose we increase the ambient pressure or increase the applied pressure. The ambient pressure was atmospheric pressure. Now, we are applying a pressure which is higher than the atmospheric pressure. Now, what we see is something like a wavy oscillation. So, the bubble as such is oscillating, but as it oscillates, we can see that the general volume of the bubble decreases first and then it increases, wavy oscillation. Okay. So, the question is that does the wall deform? So, we cannot have the wall deforming because the entire calculation is based on just unidirectional flow. The flow is rotational and incompressible. So, there is no deformation of the interface. These are only artifacts of the second order nonlinear equation that we have. Okay. Now suppose we reduce the bubble size. So, if you reduce the bubble size or increase the applied pressure or PA, what we see is that after these wavy oscillations, you see a regime where there is chaotic oscillation. Chaotic oscillations are when bubble has a radius, then it suddenly dips to almost 0, very small bubble, then again expands violently, then again contracts to a very small radius. That is what you are seeing here. Initially it is some value, then it increased to a radius, then dipped to almost 0. This is not 0. If you zoom in, it won't be 0. Okay. Then again it goes back to a very high radius and then again dips. It's like a violent collapse and growth of the bubble. Okay. Now again, if you reduce the bubble size further or increase the amplitude PA, what you see is actual bubble collapse. Bubble will grow to a height, like it will grow to a very high radius and then suddenly dip to 0. Then it will just go. The bubble has died on its own. Okay. All these are experimentally proven in case of bubbles on a pump. Okay. We loosely say that suppose there are some bubbles trapped in a reciprocating pump, there are chances of corrosion by cavitation. So, this corrosion by cavitation occurs when violent bubble collapses happen like this. Okay. Bubble collapses are accompanied by sudden release of energy and all those are for another topic, we will not be studying those, but these are all applications that the study has or Rayleigh Plesset equation has. Okay.